Hey everyone! In this video I'm going to implement a cache simulator in C++, which will include the cache itself, the main memory, a simple replacement algorithm, and simulate the processor accessing the memory system. Let's begin. The first thing I'm going to implement is the main memory class, and that's because it's independent of the other classes. I'm going to simulate main memory that has a capacity of only 4 megabytes. So I'll create a constant for the memory size. And since I can't put 4 megabytes on the stack, I'll initially have to create a pointer to an array and allocate the memory dynamically. So to do this, I'll use a unique pointer so we don't have to deal with releasing the memory at the end of the program. I'll use an std array that has an unsigned int 8 type, which represents a single address in memory. So this class will have several methods: a constructor, a destructor, and a read and write methods. The read method accepts 3 arguments. The first one is start address, the second one is the size, and the third one is a pointer to the destination buffer, where to put the data that was just read from the main memory. The reason I'm doing it this way is because the main user of this API will be the cache, and caches operate with 64-byte lines, so the easiest way to move around 64 bytes would be through a simple pointer. The write method accepts a start address, the size of the data, and the pointer to the source. It takes the data from the source and writes it to main memory. The final method will be a print method, which will help us debug and test the code. I'll create all the methods in the CPP file. The constructor of the main memory class does 2 things. The first is allocate the memory region, which is done using the std_make_unique function. This function will actually allocate the array the size of 4 megabytes. And the second step is to initialize the main memory with zeros. So I'm using the fill function to fill it with zeros. Now we get an error because we haven't included the array library. The read method reads from main memory, so it needs to copy the data from the main memory at the given start address to the destination. So to do this, I'll use an std_memcopy and put in the source, destination, and size. The write method also copies the data, but in the opposite direction. So again, I'll use std_memcopy to copy the data from the source to main memory at the given start address. The print method will be used for debugging and testing. I've tested this method before showing you this, and I found that I can fit 24 rows and 12 columns of bytes into my screen. A couple of things I forgot to include is all the libraries we need to print and format strings, so I'll add them right now. And then I can go over the rows, go over the columns, and format the string I want to print, which is a simple hexadecimal number. I'll put it in a string and send it to cout. Now I'm just adding a line at the bottom of the table so we don't get confused if we print more stuff. And that's it for the main memory class. The next thing we're going to implement is the random replacement algorithm. And to do that, we need to know the number of ways in the cache, since the victim cache line will be chosen out of a single set. So the random replacement class will have a uint8 variable called ways, which will be initialized through the setWays method. The other method in this class will be the getVictim method, which randomly chooses a victim and returns it. Let's see how we can implement this simple class. I'll just create the definitions of all the methods. And in the CPP file, I'll include the cstdlib library, which will allow us to generate random numbers. The setWays method simply sets the number of ways in the cache, and the getVictim method randomizes a number based on the number of ways in the cache. For example, in a 4-way cache, the getVictim method would return a number between 0 and 3. Later on, we can implement more complex replacement algorithms, but for this video, we'll stick to the simple random replacement. Okay, let's move on to the cache-related classes. so the cache needs to include main memory.h and replacement algorithms.h, since they will be used by the cache. I'm going to make several constants to define the properties of the cache. This will be a 16 kilobyte cache implemented on a 32-bit system, which means it will have 32-bit memory addresses. Each cache line will be 64 bytes. The cache will have 64 sets and 4 ways, making it a 4-way set-associative cache. Now I'm going to define the sizes of each part of the address. The least significant bits represent the byte offset. Since we have 64-byte cache lines, we need 6 bits to represent them. The next part of the address is the set index, which will also occupy 6 bits because we have a cache with 64 sets. The remaining bits will be allocated to the tag, which means we have a 20-bit tag. The first data structure I will create is the cache line. I'll define it as a struct with 3 fields. The first field is a tag, which will use a uint32 because we need 20 bits. The second field is data, which is implemented as an array of bytes. And the last field is the valid bit, which is initially false. The second structure I will create is the address parts, which will help us split a memory address into its parts. So it will have a tag, a set index, and a byte offset. The constructor will accept a 32-bit address and will extract the relevant bits for each field. The main idea is to shift the relevant bits to be the least significant bits and then apply some form of mask to extract the value. The next thing we'll implement is the cache set. A cache set is a simple array of cache lines. If our cache has 4 ways, it means that each cache set has 4 cache lines. The other thing I'll put here is the random replacement algorithm. And this doesn't strictly have to be in the cache set, since the random replacement algorithm doesn't store any set-related information. You could put the instance of this class in the cache, but if in the future I'll decide to switch the replacement algorithm and put another one, for example the LRU replacement algorithm, this has to be in the cache set, because the LRU algorithm stores information for each specific cache set. The cache set class will have a constructor, a destructor, a find method, and a replace method. The find method searches the cache set based on the given tag, and if it's found in the set, it returns a pointer to the cache line. If it's not found, we'll just return a null pointer. The replace method will be used when the random replacement algorithm kicks in. So to replace a cache line, we need the tag and we need the source data. Once a cache line is evicted and is replaced, the new cache line is returned. Let's create all the definitions and start implementing. So the first thing we need to do in the cache set is to initialize the replacement algorithm with the number of ways in the cache, so it knows to give us a correct random number. The find method needs to find the cache line based on the given tag. To do that, I'll go over all the cache lines in the set and check 2 things. If the cache line is valid, and if the tag in the cache line is equal to the requested tag. If both of those conditions are met, it means that we found the requested cache line, so we return a pointer to it. But if the loop completed and didn't return, we need to return a null pointer to indicate that the line wasn't found. The replace method has a couple of steps. The first step is to choose a victim line to replace. This is really easy, we just call the replacement algorithm and ask for a victim, which is a simple index. Next, we're going to the array of cache lines and accessing the victim line. I'm setting the valid bit to true, the tag to the new given tag, and the last step is to copy the data from the source to the data in the cache line. So to do that, I'll use the memcopy function again. The destination will be the victim data. The source data is the given source, and the size will be the cache line size, which in our case is 64 bytes. After that's done, we can return a pointer to the new cache line. Okay, it's time to implement the main cache class. The cache itself consists of an array of cache sets. The cache also needs a pointer to the main memory, because when a cache miss occurs, the cache itself is responsible to get the data from main memory. The cache will have three methods. The initialize method, which simply initializes the main memory pointer. The read method simply reads 32 bits from the given address. And the write method writes 32 bits to the given address. Let's create the definitions of all the methods. And in the initialize method, I'll simply initialize the main memory pointer. The first thing we need to do when reading from the cache is to split the address into its parts, so we will use our handy address parts struct to do it. Next, we need to try and find the requested cache line. So we can access the array of sets at the set index and find the cache line based on the given tag. Remember that the find method returns a pointer to the cache line. If it's not found, we'll get a null pointer. So if the cache line is valid, it means we have a cache hit. And now what we need to do is take the data, index into it using the byte offset, and reinterpret it as a 32-bit integer. The processor can request different data sizes, but to simplify things, I've only implemented a constant 32-bit data block. If the line is a null pointer, then we have a cache miss. This is a more complex procedure, so I'll list all the things we need to do before writing the code. The first thing we need to do is to find the beginning of the cache line, since the smallest block of data is a cache line, so we have to transfer 64 bytes from main memory back to the cache. The second step is to allocate a temporary data buffer to hold the data brought from main memory. Next, we need to actually read the requested data from main memory. Then, replace the cache line in the set. And finally, reinterpret the memory as a 32-bit integer, just like we did in the cache hit situation. To find the beginning of the cache line, we clear the 6 least significant bits from the address. To allocate the data buffer, we simply create an array with a uint8 type and the size of a cache line. We then read the requested data from main memory using the read method, giving it the line start, the cache line size, and a pointer to the buffer. To replace the cache line in the set, we use the replace method and give it the tag and the pointer to the buffer that has the data we just read from main memory. Once the cache line is replaced, we get a pointer to that new cache line. The final step is to go to the data field of that new cache line and use the byte offset to access a single byte. Then we reinterpret it into a 32-bit data block and return it. The write method writes the data into the given address in the cache. So the first step is to split the address into its parts. So again, we use the address parts struct to do it. We then need to find the requested line in the cache. So we access the array of sets in the relevant set index and use the find method to find the requested cache line based on the tag. If the cache line is valid, it means that we have a cache hit. So all we need to do is to reinterpret the cache memory as a 32-bit integer and write the data at the address pointed by the byte offset. Since I don't want to complicate things anymore, I'll define this cache as a write-through cache, which means it immediately writes modified data to main memory. I'll also define the cache as no write allocate, which means that if a cache miss occurs, no cache line will be allocated. The modified data will go straight to main memory. I'll call the write method of the main memory class, give it the address, the size will be 32 bits, and the last parameter is a pointer to the data buffer, which in this case is a simple 32-bit integer. By the way, if you want to understand the theory behind everything we're discussing in this video, I wrote a short 20-page ebook that explains it with diagrams and clear examples. You can find the link in the description if you'd like to check it out. Alright, So we've completed the implementation of the cache class, but now we need to implement an abstraction of the memory system. Processors don't access the cache directly. They don't actually know where the data comes from when they request memory access. So to simulate this abstraction, we're going to create another class called the memory system. This class will actually contain the main memory and cache objects as its private members. And it will define a generic interface that the processor can use to read and write data regardless of where this data is coming from. I'll add another method, printMainMemory, which will simply call the print method in the main-memory class. Let's create the definitions of the memory system. In the memory system constructor, we need to initialize the cache and pass a pointer to the main memory object. The read method of the memory system would simply forward the read request to the cache and pass it the requested address. The write method of the memory system would do the same with the write method of the cache. And the printMainMemory method will call the print method in the main memory class. Now let's create the main function and start testing this thing. I'll create a memory system object and call the printMainMemory method to see a slice of our memory. But before we start testing this whole system, I need to print messages every time the system tries to read or write data from main memory or from cache. So let's do it. I'll use the stdformat function to print reading from main memory and then also print the accessed address. I'll copy it to the write method and modify it to writing to main memory, printing the address in this case too. And then in the cache.cpp file, we need to include all the print and format libraries. I'll print the same message here too, but in the case of reading and writing to cache, I'll also add the set and the tag, which will be important when we test it. Okay, now that all the prints are in place, let's try using the system. The first thing I'll do is a simple test, which is reading from memory for the first time at address 20, and since this address is not found in the cache, we'll get a cache miss and 64 bytes will be brought from main memory into the cache. Then I'll read the same address again, and this time I expect the data to come from the cache, not from main memory. The processor.cpp file also needs all the print and format libraries, so I'll include them all here as well. Now let's print all the values from memory and see what we get. So we see that the first read does read from main memory at address 0, which is the beginning of the cache line. It reads the value 0, and then the second read actually reads from the cache at address 20, which is exactly what we expected. Next, let's test the write method. I'll write some value to the address 20, and I expect this value to be written both to main memory and cache, since the cache is right through. And then I'll read from the same address, and I expect the read to be from the cache and get the same value I wrote. Let's see what we get. So we can see that the value was written to cache and to main memory. And then, when we read from the cache, we read the correct value. The next thing I want to see is the actual data in main memory. So I'll print the main memory again at the end. And as you can see, we have the value in the bytes of the main memory. Now you probably noticed that the bytes are reversed. And this is because the least significant bits of the value are copied into the lower address, which actually makes sense. The most significant bits of the value go to the higher address, and as you can see, the value we read is the actual value we wrote, so everything works so far. The next test I'll do is writing different values to the same address. All of these writes should be written to both cache and main memory, since the cache is right through. I expect this address to be overwritten, and the only value remaining is the last one. If we read from that same address, we should get the last value written there. And as you can see, each write we perform goes to the cache and main memory. And this is the value as it's written in main memory. The final thing I want to show you is a phenomenon called cache thrashing, which is when addresses compete for the same spots in the cache. So in a 4-way cache like we have right here, each set has 4 spots. If I read 4 different addresses that have the same set index, all cache lines in that set will be occupied. In this example, I read 4 different addresses that all go to set 1, and I'll put all those reads in a loop. I expect all read requests in the first loop to be brought from main memory, because they're not in the cache yet. All following loops should read purely from cache. Main memory shouldn't be accessed. And as you can see, this is exactly what happens. You can also see I chose specific addresses so that the set will be the same, but the tag will be different. Now watch what happens if I add another read to a different address with the same set. Now we have 5 addresses competing for 4 spots. I expect the last read will cause an eviction and cache miss, which will trigger a read from main memory and a cache line replacement. And since we use a random replacement algorithm, each loop will have 1 or 2 misses that would require access to main memory. So you can see right here that the first memory accesses are all from main memory, but then it starts reading from cache, but it's not all pure cache. You can see that there are many cache misses here, which reduces the cache hit rate and degrades performance. Thanks for watching. If you'd like to support the channel and dive deeper into how CPU caches work under the hood, my ebook is a great place to start. It's packed with illustrations and examples. The link is in the description. I'll see you soon.